Hello, everyone. Today we're going to dive into a new and powerful mathematical tool, logarithms. By the end of this lesson, you will be able to define what a logarithm is and convert between logarithmic and exponential forms. We'll be covering section 1C, which is all about logarithms. Now, you're already familiar with solving certain types of equations. For instance, if I asked you to find the positive value of x for which x squared equals 5, you'd know exactly what to do. For the equation x squared equals 5, you would use the square root function. You'd take the square root of both sides to find that x is the square root of 5, which is approximately 2.236. The square root is the inverse operation of squaring. But what if the unknown x is in the exponent? Consider this equation. What if we have 10 to the power of x equals 5? How do we solve for x here? We need an inverse operation for exponentiation. That inverse operation is the logarithm. A logarithm is the function that lets us find the exponent. In this case, we would say that x is the logarithm with base 10 of 5. We write this as x equals log base 10 of 5. Using a calculator, we find this is approximately 0.699. This means that 10 raised to the power of 0.699 is about 5. This leads us to the fundamental definition of a logarithm, which is crucial to everything we'll do next. This is the key relationship you must remember. The equation a equals b to the power of x is equivalent to, or the same as, saying that the logarithm of a with base b is equal to x. Let's break that down. The logarithm gives you the exponent. So log base b of a is asking the question, to what exponent x must we raise the base b to get the number a? The answer is x. Let's state that again. The expression log ba x is the logarithmic form, and a equals b that x is the exponential form. They are two ways of saying the exact same thing. In this notation, b is called the base of the logarithm and a is called the argument. While we can use any positive number other than 1 as a base, the most common base you'll see is base 10. This is called the common logarithm. Because it's so common, if you see a logarithm written without a base, like log x, you should assume the base is 10. So log x is just a shorthand for log base 10 of x. One final important point. Think about the expression 10 to the power of x. Can this ever be negative? No. No matter what real number you choose for x, 10 to the x will always be a positive number. Since 10 to the x is always positive, it means there's no answer to a question like what exponent gives -2. You can't raise 10 to any power and get a negative result. Therefore, the argument of a logarithm must always be a positive number. You can only take the log of a positive number. So to recap, we've defined the logarithm as the inverse of an exponential function. The key takeaway is the equivalence. A equals b cr x means the same as log b a equals x. Now you can define logarithms and switch between the two forms. Now that we understand the definition of a logarithm, let's practice calculating some simple logarithms without a calculator. In this scene, our goal is to calculate the value of logarithms by converting them into their exponential form. Let's look at our first worked example. We need to calculate the value of log 1000 without a calculator. The first step is to set the expression equal to a variable, let's say x. So we write x equals log 1000. Now what's the base here? Since it's not written, we know it's the common logarithm, which has a base of 10. So this is really log 10 1000. Let's write that in explicitly. X equals log base 10 of 1000. The next step is to use our key definition to convert this logarithmic equation into its exponential form. Remember, log ba equals x is the same as b through x equals a. Applying this, our base b is 10, our result x is x, and our argument a is 1000. So we get 10 to the power of x equals 1000. Now we have a much simpler problem. We just need to figure out what power of 10 gives us 1000. We know that 10 times 10 is 100, and 100 times 10 is 1000. 1000 is 10 cubed. We can rewrite the equation as 10 to the x equals 10 to the 3. Since the bases are the same, the exponents must be equal. Therefore, x must be 3. So the value of log 1000 is 3. We've successfully calculated a logarithm by thinking about it as an exponent. Let's try another one to make sure we've got it. Let's calculate log base 3 of 27. We want to find the value of log base 3 of 27. First, we set it equal to x. Second, we convert to exponential form. The base is 3, the exponent is x, and the result is 27. So 3 to the power of x equals 27. Now we ask, what power of 3 is 27? Well, 3 times 3 is 9, and 9 times 3 is 27, so 27 is 3 cubed. We can write this as 3 to the x equals 3 to the 3. Therefore, x equals 3. So log base 3 of 27 is 3. We have now achieved our objective. We can find the value of a logarithm by setting it equal to x and converting the equation to its exponential form to solve for the unknown exponent. In the last scene, we found the value of a logarithm. Now we'll flip that around and solve for a variable that's inside a logarithm. Our objective is to solve basic logarithmic equations by converting them to exponential form. Let's work through this example. We need to find the exact value of y if the log base 10 of the quantity y plus 1 is equal to 3. The equation is already in logarithmic form. Our strategy is the same as before. Convert it to exponential form to free the variable y from the logarithm. Let's identify the parts. The base b is 10. The argument a is the entire expression in the parentheses, which is y plus 1, and the result x is 3. We have our base, our argument, and our exponent. We will now use the relationship a equals bx. Plugging in our parts, the argument y plus 1 equals the base 10 raised to the exponent 3. So y plus 1 equals 10 cubed. Now we have a simple algebraic equation. First, let's calculate 10 cubed. 10 cubed is 10 times 10 times 10, which is 1,000. So our equation is y plus 1 equals 1,000. To find y, we just need to subtract 1 from both sides. Subtracting 1, we find that y equals 999, and that's our exact answer. Let's do one more to solidify this. Let's solve log base 2 of x minus 5 equals 4. We want to solve log base 2 of the quantity x minus 5 equals 4. Again, we convert from logarithmic form to exponential form. The base is 2, the exponent is 4, and the argument is x minus 5. This gives us the equation x minus 5 equals 2 to the power of 4. First, we evaluate 2 to the power of 4. That's 2 times 2 is 4, times 2 is 8, times 2 is 16. So x minus 5 equals 16. Finally, we add 5 to both sides to get x equals 21. So we've met our objective. We can now solve for a variable inside a logarithm by converting the equation to its more familiar exponential form and then solving algebraically. So far, we've focused on the common logarithm, base 10. Now we'll introduce another extremely important base. In this scene, you will learn about the number e and the natural logarithm, and you'll be able to solve equations involving it. Another very common base for logarithms is the number e. Like pi, e is a special irrational number. Its value is approximately 2.71828, and its decimal representation goes on forever without repeating. The number e is fundamental in mathematics and science, especially in topics related to growth, decay, and calculus, because it's a very special rate of change. We'll explore that more in later chapters. A logarithm with base e is called the natural logarithm. To make things simpler, we don't write log base e of x. Instead, we use a special notation, ln x. So whenever you see ln, it just means log base e. Let's see how to work with this in an example. Our goal is to rearrange an equation to make x the subject. We're asked to make x the subject of the equation. The natural log of the quantity 3x minus 2 equals y. The process is exactly the same as before. We just need to remember that ln means the base is e. First, let's rewrite the equation explicitly with the base. The natural log of 3x minus 2 equals y is the same as log base e of 3x minus 2 equals y. Now, we convert this logarithmic equation to its exponential form. The base is e, the exponent is y, and the argument is 3x minus 2. Using our rule, we get 3x minus 2 equals e to the power of y. Our goal is to isolate x. This is now a straightforward two-step algebraic problem. First, we'll add 2 to both sides. This gives us 3x equals e to the y plus 2. The final step is to divide both sides by 3, and we have our answer. X equals the quantity e to the y plus 2, all divided by 3. We have successfully made x the subject. To recap, we've introduced the natural logarithm, ln, which is just a logarithm with the special base e. We've seen that solving equations with ln follows the exact same procedure of converting from logarithmic to exponential form. You are now equipped to handle these types of problems. Welcome back. In this segment, we're going to look at how standard algebraic rules apply to expressions involving logarithms. Our objective is to simplify algebraic expressions containing logarithms. Sometimes you'll encounter expressions where logarithms are treated just like variables. Let's look at an example. We need to simplify the expression 3 times the natural log of x minus the natural log of x, all divided by the natural log of x. This might look complicated, but the key is to recognize that ln x is just a number. We can think of it as a single entity, like a variable. Let's try substituting it with y to see the structure more clearly. If we let y equal ln x, our expression becomes 3y minus y all over y. This is a much simpler algebraic fraction. Now let's simplify this expression with y. First, we simplify the numerator. 3y minus y is just 2y, so the expression simplifies to 2y divided by y. Now we can cancel the y from the top and bottom, which leaves us with just 2. Since our original expression was equivalent to this one, its value must also be 2. Let's show the steps again, but this time using ln x directly. Starting with the original expression, we first focus on the numerator. We have 3 of something minus 1 of that same something, so 3 ln x minus 1 ln x is 2 ln x. The expression becomes 2 times the natural log of x divided by the natural log of x. Now we have the term ln x in both the numerator and the denominator. We can cancel them out. Dividing the top and bottom by ln x, we are left with the final answer, 2. As you can see, we've met our goal. We can simplify expressions with logarithms by treating the logarithm term as a single algebraic unit and applying the standard rules of algebra, like combining like terms and canceling. In this lesson, we'll explore the powerful inverse relationship between logarithms and exponentials. By the end of this scene, you will be able to use the inverse properties of logarithms to simplify complex-looking expressions. Since the process of taking a logarithm is the reverse of raising to a power, one operation undoes the other. This gives us some very important results. Let's look at key point 1.5, which covers these inverse properties. For the common logarithm, base 10, first, the log of 10 to the power of x is just x. The log undoes the exponentiation. Second, 10 raised to the power of log x is also just x. The exponentiation undoes the log. The same exact logic applies to the natural logarithm, base e. The natural log of e to the power of x is x, and e raised to the power of the natural log of x is also x. These properties are extremely useful for simplifying expressions. Let's see these properties in action with an example. We need to find the exact value of e raised to the power of 3 times the natural log of 2. At first glance, this doesn't perfectly match our property e of ln x equals x because of the 3 in the exponent. We need to manipulate the expression first using a law of exponents. Recall the power of a power rule. A to the power of m times n is equal to a to the m, all raised to the n. We can apply this to our expression. Here a is e, m is ln2, and n is 3. So e to the power of 3 times ln2 can be rewritten as e to the power of ln2 with the entire thing raised to the power of 3. Now look at the expression inside the parentheses e of ln2. This perfectly matches our inverse property e third ln x equals x. Using this property, e to the power of ln2 simplifies to just 2. Now we can substitute the simplified value back into our expression. Our expression becomes 2 cubed, and 2 cubed is 8. So the exact value of e to the 3 ln2 is 8. We've successfully met our objective. By using a law of exponents combined with the inverse property of logarithms, we were able to simplify a complicated expression to a simple integer. This shows just how powerful these properties are. Hello. While we can calculate some logarithms by hand, most require a calculator. In this scene, you will learn how to use your graphical display calculator, or GDC, to evaluate logarithms and how to present your answers in the correct format. We'll be focusing on the numerical evaluation of logarithms using technology. Your calculator will have buttons for both the common logarithm, log, and the natural logarithm, ln. Let's work through an example. The task is to use a calculator to find the value of the natural log of 345,678. We need to give the answer in 2 specific formats: rounded to 3 significant figures, and in standard index form. First, let's get the value from the calculator. You would type ln, then 345,678, and press enter. Your calculator display should show something like 12.75326,298. Now for the first part of the answer. rounding to three significant figures. Significant figures are the first non-zero digits of a number. In our number, the first significant figure is 1, the second is 2, and the third is 7. To round to three significant figures, we look at the fourth digit. The fourth digit is 5. The rule is, if the next digit is 5 or greater, we round up the last significant figure. If it's less than 5, we leave it as is. Since the next digit is 5, we round the 7 up to an 8. So our number rounded to three significant figures is 12.8. Now for the second part of the answer, converting to standard index form, which is also known as scientific notation. Standard index form requires writing the number as a product of a number a between 1 and 10 and a power of 10. Our number is 12.8. To get it between 1 and 10, we need to move the decimal point one place to the left, making it 1.28. Since we made the number smaller by one factor of 10, we have to multiply by 10 to the power of 1 to keep the value the same. So 12.8 in standard form is 1.28 times 10 to the 1. So we have successfully used our calculator to find a logarithm and then formatted the answer correctly, both by rounding to significant figures and by converting to standard index form. You are now ready to use your calculator to tackle more complex logarithmic problems. We've now arrived at one of the most important applications of logarithms, solving exponential equations. In this scene, you will learn how to solve for an unknown variable when it's in the exponent. Our focus is on solving exponential equations, where the variable we're looking for is a power. Let's start with a straightforward example. We need to solve the equation e to the power of x equals 4. There are two common ways to think about this. The first is to directly convert the exponential equation to its logarithmic form. Remember, bx equals a is equivalent to log b equals x. In our case, the base b is e, the argument a is 4, and the exponent is x. Converting to logarithmic form, we get log base e of 4 equals x. And of course, log base e is the natural logarithm, so x equals the natural log of 4. This is the exact solution. The second method, which is very powerful, is to take the logarithm of both sides of the equation. Starting with e to the x equals 4, we can take the natural log of both sides. This gives us ln of e to the x equals ln of 4. Now we use the inverse property we learned. Ln egrex simplifies to just x. This leaves us with x equals ln 4. Both methods give the same exact answer. The question asks for the answer to three significant figures, so we use a calculator. The natural log of 4 is approximately 1.3862. Rounding to three significant figures, we look at the 8, then the 6. Since 6 is 5 or greater, we round the 8 up to 9. So x is approximately 1.39. Let's try another one, this time asking for an exact answer. We need to solve 10 to the power of x minus 2 equals 21. Since the base is 10, it makes sense to use the common logarithm. Let's convert this to logarithmic form. The base is 10, the exponent is the entire quantity x minus 2, and the result is 21. This gives us log base 10 of 21 equals x minus 2. Our goal is to solve for x. All we need to do is add 2 to both sides of the equation. This gives us our final exact answer, x equals 2 plus the log of 21. We leave it in this form because the question asks for the exact solution, not a decimal approximation. We have now met our objective. You can solve exponential equations by converting them to logarithmic form or by taking the logarithm of both sides, allowing you to find both exact and approximate solutions for an unknown exponent. In our last scene, we solved basic exponential equations. Sometimes, however, equations need to be rearranged first. In this final lesson, you will learn how to solve more complex exponential equations that require algebraic manipulation before you can apply logarithms. Let's tackle this problem. Solve e to the power of 3x plus 2 equals 4 times e to the x. Notice that this equation isn't in the simple form by equals a. We have exponential terms on both sides. There are a couple of ways to approach this. Let's explore the method suggested in the textbook first. The strategy is to express everything as a power of e. The left side is already a power of e. On the right side, we have 4 times e to the x. We can rewrite the number 4 as a power of e using the inverse property. Remember that e is through of ln a equal to a, so we can write 4 as e to the power of the natural log of 4. Now, let's substitute this back into our equation. The equation becomes e to the 3x plus 2 equals e to the ln 4 times e to the x. On the right side, we are multiplying two powers with the same base, e. We can use the exponent rule, a m equals a to the m plus n, to combine them. So the right side becomes e to the power of ln 4 plus x. Now we have a much nicer equation. We have a single power of e on both sides. Since the bases are the same, the exponents must be equal. This allows us to set the exponents equal to each other. 3x plus 2 equals ln 4 plus x. This is just a linear equation. We need to gather the x terms on one side and the constant terms on the other. Let's subtract x from both sides and subtract 2 from both sides. This gives us 2x equals ln 4 minus 2. Finally, we divide by 2 to get the exact solution for x. The question asks for the answer to 3 significant figures, so we'll use a calculator. Plugging this into a calculator, we get approximately negative 0.307. Now let's look at an alternative method, which is often more direct. The idea is to first isolate a single exponential term. Starting again with our original equation, let's try to gather the exponential terms on one side. We can do this by dividing both sides by e to the x. This gives us e to the 3x plus 2 divided by e to the x equals 4. Now we use the exponent rule for division, a m minus n. The exponent becomes 3x plus 2 minus x, which simplifies to 2x plus 2. So our equation is now e to the power of 2x plus 2 equals 4. This looks much simpler. It's now in the form we know how to solve. We can take the natural log of both sides. Taking the natural log of both sides gives us 2x plus 2 equals the natural log of 4. Solving for x, we subtract 2 and then divide by 2. This leads to the exact same solution as before. Both methods are valid, and you can choose whichever one you find more intuitive. We have now achieved our final objective for today. You can now solve complex exponential equations by first using algebraic and exponent rules to simplify them, and then applying logarithms to find the solution. This is a critical skill in mathematics and its applications.